when it comes to times of using kernel memory, that is another library from Microsoft, is a spin-off from semantic kernel, and it's dedicated to RAG, retrieval augmented generation. And when it's time to extract text from a PDF file, as an example, because PDF is probably the most widely used form of documents, it becomes something a little bit difficult because, it's quite simple to extract text from PDF, but usually base low-level extractor are pretty much stupid and extract simple text. And PDF is not exactly the most perfect format for extracting structured text, because the main purpose of a PDF file is having the file to be represented in your monitor, in a printer, in any printer, in the very same way. So it is a format pretty much concentrated on layout of the document. So for example, if you have a table, the table usually is just text placed in the page and a series of lines that draw the table. So when you extract text, you usually lose the structure. And so how can we use a better extraction tool for having something that is much more useful to us? And I'm going to show you some techniques that are not related to semantic kernel, but in my opinion, kernel memory is just a part of semantic kernel. So we are moving a little bit on the RAG side of the situation. And I want to show you in this video how you can use an external service called LLAMA Cloud to extract the text in a much more smart way. Configuration of kernel memory is really similar to semantic kernel. First of all, you need to use Nugget packages called Microsoft Kernel Memory. That's pretty much pretty self-explanatory. So you just go in to install this package. Then you can start to configure kernel memory. Actually, you can configure a lot of stuff, but basically you can use, first of all, an embedding config. And that is because the main form of searching for kernel memory is vector searching. So you need to specify which kind of model you're going to use to extract vector from text. This is a very old example. So you see, I'm still using the text embedding ADA, the ADA. It's now OpenAI is much more smarter and modern way of embedding, but you can use whatever you want. It is configurable. And as usually, you need to specify the model, the OpenAI key, and the Azure endpoint, because I'm using OpenAI exposed by Azure. Now, kernel memory does not use only the embedding part that allows you to embed a text, a vector from text, but use also a chat config that is the large language model that will be used for the AG part of the RAG. So the large language model used to pass the fact and get an answer. In this situation, it's very similar to semantic kernel. Just specify the endpoint, just specify the deployment name, the API key, and pretty much equal to semantic kernel, just configuration. After you have the config, you simply configure a kernel memory builder specifying the embedding config and the text generation config. And then you need to specify one object storage and one vector storage. For this example, I'm using the standard simple file storage config and simple vector DB config. These are absolutely not to be used in production because they are not production code. These two versions of databases use a simple file storage to store information. And they are really useful for me to explain what is happening under the hood to specify, to demonstrate you how you can have a better extraction. Now, I'm going to extract text from a document that has structured images. This is the model of the robot, cleaner robot that I have in my house. And as you can see, that is a pretty much complex document with images, complex layout. And so I'm going to show you what happens if you use the base kernel memory extraction and what is got into your store. To interact with kernel memory, you just use a kernel memory builder to build a memory serverless, and then you can index documents simply using the import document sync function, and that is using the pretty much standard pipeline, and it's going to go into extract text and store inside the file system-based database. And that is the structure of the object database where the kernel memory stores the original file and then have the extract.txt and extract.json that contains data of the extracted test. And then you see you have 0, 1, you have all the chunk because a part of RAG text is going to be split into chunk of document, and each chunk of document is passed to the embedding provider to get a vector representation to be stored in vector storage. So that is the basic situation. And let's see what is in the text. That is the simple content extracted, and it's all the text of the manual with a little formatting. You see you have dots. Basically, the basic implementation of kernel memory is doing what it can to extract everything. But as an example, it does not extract images. But that's not the only problem. The problem is this text is absolutely not structured. So when you separate in chunk, it becomes probably difficult to understand which is the best way to use chunking, okay? So probably the best way is to have a different tool, a much more modern tool to extract structured tests. LLAMA Cloud is a cloud service that allows you to do some functionality. It offers you some functionality through an API for doing RAG because Llama index, it's a library in Python used to create RAG. And it has a nice functionality called parse, in which not only you have an instrument that is able to extract structured text from your PDF or from every format of the file, but it uses in the background a large language model so you can give a specific instruction on how you want it to extract your text. Let's see an example because I've integrated with a very few lines of code into kernel memory, and it's very easy to use and it's very easy to extend, so it's pretty much powerful. The example is pretty much the same example as before, but this time when I configure everything, I use in the kernel memory builder with content decoder, LLAMA Cloud parser document decoder. So kernel memory is highly expandable library because it's highly modular. And in this situation, I have wrapped the call to the LLAMA Cloud parse service. It's a simple REST API in which you can upload a document and then ask stuff. So as you can see, I have a previous configuration when I'm using my Llama API key that allows me to use the service. The service, it's pay for your service. It has a cost. It gives you a key with a certain amount of code that is free, and then you're going to pay if you want to use it, but it worth the money. And then I'm simply creating, as you can see, the cloud parser configuration and the Llama Cloud parser client. That is a simple HTTP client-based C# code that allows me to call the API and get the result back. And as you can see, very few lines of code. I've configured kernel memory with a new content decoder, and a content decoder is a piece of kernel memory that is able to take a binary file and extract text from it. And the question is, how complex is to write a decoder? Well, it's pretty much easy. So you need to implement the iContent decoder interface from kernel memory. Then you have all your constructor with all your parameter that you need to use. And that is how you construct your class. In my situation, I just need a Llama Cloud parser client that is small wrapper I wrote around the Llama API just to make easier to call the API. Then you need to implement the subports MIME type that basically is the way kernel memory asks to your custom decoder and say, hey, which kind of MIME type of document you're gonna decode? And I'm simply say, I wanna say that if MIME type start with PDF or open document text. So you can use pretty much any MIME type that your custom decoder supports. So since Llama Cloud supports PDF or support doc file, it supports many type of file, you will specify into this function all the type of document you want to be directed to this kind of document decoder. Now in the decode async function, you see that's pretty much the decode async function. I'm using a custom class. You can look at the code in my repository. It's nothing complex. It's just an HTTP call to the Llama Cloud. What is really, really interesting is that I will use the context provider get context function. And the context provider is something that is bring you from the kernel memory infrastructure, because when I'm gonna extract a document with llama index, I want to be able to specify a specific instruction on how I want llama cloud to extract text from my document. And so since this is a parameter that change for potential every call I do, every document I'm indexing, I can use context provider to specify something in a context. And in my situation, I have two important parameters. The first one is the file name key, because I like to specify to Llama Cloud what is the name of the file, because it is gonna use it, and also which are potentially parsing instruction. And then as you can see, I'm creating an upload parameter. I'm going to create a call and simply call the Llama Cloud API. Very simple code, just use an HTTP call. Then I come back to the kernel memory code, because the code I'm using this time it's a little bit different. First of all, okay, I'm simply create a build service provider, and I get the required Llama Cloud parser client that's allow me to verify that I'm able to construct the Llama Cloud parser client from the service provider. This is not a code that you really need to code. It's important to understand that everything is registered correctly in the inversion of control of my example. Then you build the memory serverless as usual. But now I need to get the orchestrator and all the decoders. So internally, kernel memory has the concept of orchestration, that it's a pipeline orchestrate what I need to do with a document. So you need to extract text, chunk text, pass all the chunk to an embedding provider, store in the vector store, etch. So it's a series of steps. So as you can see, you can access the orchestrator, and I can take all the services of the type iContent decoder to see in this configuration of kernel memory which are all the decoders I configured. Then, as you can see, you can verify that I have a series of handler like this. The text extraction, it's called it uses the orchestrator, and it passes all the decoder I've configured in my system. And then you have text partition. So that's how kernel memory use the pipeline to the code content. And it's here just to show you how everything can be configured. So that I'm recreating the standard pipeline. Then I have a pipeline builder in which I build all the steps I need to do for the pipeline. And the only difference in this example is that the partitioning strategy, so the part of the code that chunks the text into smaller chunk, is a custom markdown partition. And we will see how this is created in the next video, but it's important to understand that I've changed the extraction, the text chunker, for a reason, because I will also change how Llama Cloud extract text. And that's done in the latest part, in which I'm adding the add Llama Cloud parser option, in which I'm specifying not only the file name and the context provided its basic code from kernel memory, but I'm going to specify instructions. I've already performed the call, because as you can see, it requires 38 seconds. It's an online service that requires time. But what is important is this section. When I'm creating the Llama Cloud parser option, what I do is I specify an instruction. This is manual for a dreamy vacuum cleaner. I need you to extract a series of sections. So what I want it to do, it's not simply extract text, but I'm specifying that this text is going to be used by a call center, by an help desk, to solve user questions. So I'm asking to the large language model that's behind the Llama Cloud parser service to extract text in a specific format I'm giving. And the format is, I want a small section of question, answer. So the purpose is, I'm giving you a document, extract a series of question and answer. That is important because the same document can be passed multiple times to this kind of services, each time extracting different information. In this scenario, I'm only interested in a series of question and answer. And after I configure everything, I simply build the pipeline builder I've configured before, And the pipeline builder contains not only the name of the local file that is going to be parsed, but all the steps I want to perform on this file. And then I simply run pipeline async. And as you can see from the bottom part, it is going to contact the LLAMA Cloud service, and it is asking, hey, that's the file, that's our destruction, give me a markdown text. Now, after the extraction is complete, you can see that I have the same manual dreamy.pdf.extract.txt that represent the text extracted from the file. But look at this. Now the text is a formatted I've decided. I've asked the large language model, please extract question answer, separate its question and answer with a specific piece of code, 3 dashes, use markdown. And so what I have is not only structured extracted text, because this is much way better than the previous version where I have text intermixed with a footer and everything is a little bit messed up. Now I have very highly structured text, but not only, I had used a large language model behind the scene by llama parser that allows me to specify its structure. So I've not extracted the original text from the file. I've extracted a summary, a transformed version of the text that it's used by me for a specific scenario. So when I'm going to index in a vector database or in any other database, this kind of text, this is much more useful for me because I'm going to use it for an help desk, for a call center. So I have a series of answer and question. And as you can see, having this kind of text extracted from a PDF will help tremendously you to improve the quality of the answer of your RAG system. And this is done with a simple call to an external service. It's going to cost you a few bucks, but you can really get highly formatted text, good formatted text, and what you really need to index inside your database. And this concludes the example in which I show you how easy it is to extend kernel memory with a custom content decoder for changing the way kernel memory extracts text from a file, like a PDF file. In this example, I've shown you how to use an external service like LLAMA Cloud that not only extracts text from the file you give it, but it also uses behind the scene a large language model so you can specify a very detailed instruction on what you want to get extracted from the document. And I show you an example in which I give a manual of a product, and what I want extracted, it's not the text of the manual, but a series of question and answer extracted from the manual that I can use in a help desk. So it's very much more powerful way to extract document, and that brings from the power of the large language model. So please, if you need to create a RAG system that has some specialized stuff, some specialized document like product manuals, please do not rely on standard text extracting because your RAG system is going to perform poorly. Please extract some services like this that can allow you to extract highly structured text data, highly contextualized and structured text data, because it's going to help tremendously you in having a better answer from your RAG system. Bye-bye. I'm waiting you in the next video of the series in which I complete this example showing you how you can use a custom chunker that is based on the format you asked to the large language model. Bye-bye. Waiting you for the next video.